In this video, we're going to work through some application problems involving vectors. And if we can draw a very accurate diagram, a lot of these problems are pretty simple to solve, especially when we're using some vector properties. So let's look here at this first one. We want to find the work done by lifting a 100-pound bag of potatoes 3 feet. Now, work, I wrote the equation for us. So work is equal to force times distance times the angle between force and direction. And we're not going to convert our units. We're going to stick with the units that they gave us, which is in terms of the weight of the bag is 100 pounds, and we're moving 3 feet. So our diagram is actually very simple here. We have the ground, and we have our bag of potatoes. Now, our bag of potatoes is 100 pounds. And we just want to find the work done by lifting the bag of potatoes 3 feet. So the bag of potatoes is moving this direction, and it's moving that direction 3 feet. Now, because it says it's lifting, we're not technically pulling on it in any direction. Our force is going to be going parallel to the direction of travel. So theta, the angle in between the force and the direction of travel, is actually 0 here. And so to find the work done, work is going to equal force, which really we're just pulling 100-pound potatoes, so it'd be 100 pounds times 3 feet times cosine of 0 degrees. And that's going to give us 300 foot-pounds. 300 foot-pounds. All right, let's go look at a different one. All right, a ship is heading due north at 12 miles per hour, and the current is flowing southwest at 4 miles per hour. Find the actual bearing and speed of the ship. All right, so I'm going to draw north, south, east, west lines here, so we can see what's going on. So we have east, south, west, north. And so we have our ship is heading due north at 12 miles an hour. So I'll let the ship here be green. So due north, 12 miles per hour. So that's going to be a vector. We're going to start at the intersection of the north, south, east, west lines. And here is my ship. All right, so my ship is right there in green. At the same time, the current is flowing southwest at 4 miles per hour. All right, so southwest, 4 miles per hour is my current. Well, I don't want to apply that from the intersection of the north, south, east, west lines. I don't want to put that there because I want to find the resultant vector. So what I have to do is, from the end point, because we connect vectors from head to tail, from the end point of this vector is going to be the starting point of my current. Now, I can draw another set of east-west lines to kind of help me with my placement here. And so it's going southwest, so that's exactly halfway between the west and where the south line would be. So my current is going perfectly this direction. So here's my current. Now, the resultant vector is going to go from where my ship started to the end point of the current. So my resultant vector goes from start to finish right here. So there's my resultant vector. And so we kind of see that this ship is going to be headed in the direction kind of slightly west of north. And so we see what we have our diagram. Now you could actually solve this using triangles and not vectors, but I'm going to take a vector approach. So the resultant vector here is going to equal the sum of the ship's vectors and the current vector. All right, so let's find the individual vectors for the ship and the current. So the ship, its current, it is heading due north. So when I'm writing the component form, it has no horizontal component, so the horizontal component is going to be 0. And it's going north at 12 miles per hour, so I'm going to let that be 12 for the y component. Now my current here, it's going 4 miles per hour in the direction of southwest. Now remember, when it comes to vectors, our direction angle is off the right hand side of the x-axis. So I'd have to start from the kind of the east line and come all the way over and say, okay, that's going to be what theta is, which southwest is halfway in quadrant 3, so that's going to be 225 degrees. So our current is going to be its magnitude, cosine of the direction angle, by magnitude sine of the direction angle. All right, so there's the vector of the current. And so our resultant vector for the ship with its heading and the current is going to be the sum of those two vectors. So 4 cosine 225 by 12 plus 4 times sine of 225. And that's going to give us the resultant vector, which is negative 2.83 by 9.17. Now, in context of what these numbers means, it means that it is heading west at 2.83 miles per hour, while at the same time it is heading north at 9.17 miles per hour. So it looks at in terms of how far, in this case, how fast is it going left to right versus up and down in context of a coordinate plane, not necessarily north, south, east, west. And so now we want to find the actual speed and the bearing. All right, well, speed is equal to the magnitude of our vector here. All right, so that's going to be the square root of negative 2.83 squared plus 9.17 squared. And that's going to give us 9.6 miles per hour. So that's our speed. Now we want to find the bearing of the ship, or the, let's say, the direction it's heading. So we know this vector's heading over in quadrant 2. And so, we know the ship. I have north, I have west here. It's going kind of this direction here. So let's find the angle it makes between the west line here, which we know its vertical component is 9.17 and the horizontal component is negative 2.83. So we use tangent, and so tangent of theta is equal to opposite over adjacent. I'm going to keep all the signs positive. So 9.17 divided by 2.83. And I would do inverse tangent, and that's going to give me theta. So theta here is 72.85. Now I can actually use that to give a direction measure of a ship, because that is the number of degrees north of west. I could also take that same measure and say, okay, well, usually if you're given your direction angles like in that kind of style, you want to use a smaller number, which I would go find the angle between that and that vector in north. I'd subtract the 72.85 from 90, and that's going to give me about 17.15. And I could also give this direction as 17.15 degrees in the direction of west of north. They tell me the same thing. But the problem specifically said bearing. Bearing. Bearing is the number of degrees rotated clockwise off due north. And so we're looking at our diagram and say the bearing angle is going to be off due north all the way around to R. That's my bearing. Well, our bearing in this case, looking at how it rotated, I would need to go 270 degrees plus the number of degrees we are in quadrant 2, which we said was 72.85. And so our bearing angle is 342.85. So we have multiple ways here to describe the direction, and it's just based on what the problem tells us. If it specifically says bearing, we'll have to use what's in orange. If it just says what's the direction, it's kind of up to us as long as we have described the angle in terms of relativity to maybe north, south, east, or west. All right, on to the next one. All right, so here we have a plane, and it's heading, It's heading due east, 250 miles an hour. All right, and then I have the wind is blowing from the northeast. So let me give us a picture here of what's going on. Now, so my plane is heading due east. So I'll make my north, south, east, west lines. All right, so west, east. My plane is flying due east, 250 miles per hour. So plane's trying to do that. There's my plane. Now, I may as well go ahead and write the vector for the plane. So the plane vector here is going due east, so the 250 is going to be the x component, and it has no y component. Now at the same time, we're having our wind applied to it, and we have to connect our vectors head to tail. So from the end point of the vector, I could make another set of north, south, east, west lines, and I'm just going to use the current east-west line. And the wind, 25 miles per hour, is blowing from the northeast. So that doesn't mean I push it into the northeast. It's coming from that direction, so it's actually blowing in the direction of southwest, which, like the previous example, if it's blowing southwest, that means the overall angle here for theta is going to be 225. So the component form of my wind would be magnitude, so 25, cosine of that angle, so cosine of 225, by magnitude sine of that angle. And the resultant vector is going to equal the addition of the plane and the wind. So R is going to equal plane vector plus wind vector. So I just have to add those two together. And then we can worry about finding ground speed and the direction. So R is going to equal, add the x components together, so 250 plus 25 cosine 225. And then the y component, because the plane had 0, would just be 25 sine 225. Right? And so we type that into our calculator and get the components of R, and we get a horizontal component of 232.32 and a y component of negative 17.68. And so now let's find the speed. Well, the speed of the plane is going to equal the magnitude, which is going to be the square root of the x component squared plus the y component squared. And that's going to give us 232.99 miles per hour. All right, so the wind has slowed the plane down by about 17 miles an hour. Now let's find the direction of the plane. Well, we're zooming in here, all right, so that way I don't have to draw this thing again. I see my plane off my plane's vector. All right, let's find the angle it makes between the x-axis right there, which we'd have the y component of the resultant vector, and we have the x component to work with. So for the direction of the plane, we're going to use tangent. So tangent of theta is equal to, keep the components positive, so y over x, so 17.68 divided by 232.32. Then we use inverse tangent, and we'd get theta here. So theta would equal 4.35 degrees. Now, that is the angle between the resultant vector and due east. So I could go ahead and use that as my directionary measure and say, okay, well, I pushed the plane down in the direction of south of east. I could also convert this into a bearing if I wanted to. Some people like the bearing measures. So bearing, remember, is clockwise off due north. So I'd start at due north, go in the clockwise direction for my bearing. So that would be 90 degrees plus theta, so 94.35 degrees. All right, let's go look at another one. All right, so this one here, just trying to give some different types of problems. All right, we have a disabled snowmobile, and it can be pulled by a force of 120 pounds that's parallel to the ground. I want to know what force, or what's the magnitude of the force that needs to be applied at an angle 25 degrees to the ground to move this snowmobile. All right, so let's say, here's my ground, and I have my snowmobile here. All right, so there's my snowmobile. And I'm told that it can be pulled by a force of 120 pounds. So if I have this vector of 120 pounds that's parallel to the ground, that snowmobile will move. Well, you want to know what force has to be applied at an angle of 25 degrees to that vector. Well, I would not come to the end point here and draw my force vector there. The reason why I won't do that is because I'm not adding the two vectors together. I want to know, well, what's the magnitude of F going to have to have that horizontal component? So I'm going to draw a vector from the edge of the snowmobile, and the angle in between them is 25 degrees. Now, because the black vector, the 120 pounds, is parallel to the ground, this is going to form a 90. And so we want to know the magnitude of this force vector. Well, you would use the cosine function because you have angle, adjacent, hypotenuse. So cosine of 25 degrees is equal to adjacent divided by hypotenuse. And I would solve for F. So the magnitude of this force is going to equal 120 divided by cosine of 25 degrees, which is going to give me 132.41 pounds. All right, new problem. All right, John is sitting on a sled on the side of an iced over hill that is inclined at 60 degrees. The combined weight of John and the sled is 160 pounds. What's the magnitude of the force required to prevent the sled from going down the hill? Okay, so I have to draw this picture a little differently here. So I got to draw my inclined plane. All right, so to do that, I have a horizontal, and then I'm going to have my inclined plane. And the angle of incline is 60 degrees. Now I have to put John and his sled on the hill, and I'm just going to make a box. All right, so There's my sled. The combined weight of John and the sled is 60 pounds. All right, when you're drawing these kinds of pictures, all right, so the weight is 60 pounds. We have to use some physics here where weight is determined by mass and gravity. So from the center of the box here, I'm going to draw a vector that acts in the direction of gravity. So I'm going to pull this thing straight down. Well, try to go straight down anyway. All right, so this is the weight. Or if we want to, we can call it gravity. How about we do that? Call that G for gravity. And we know that's going to be 160. All right, so that's 160. Now, at the same time, the sled, all right, if I'm actually sitting on a plane, I have gravity acting on me, and I am pushing against a surface. And the surface itself is acting back into the object that is pushing on it. So there is also a vector that is pushing perpendicular to the surface back up through the object, which is called a normal force. And so what I can do is, since the normal force is actually pushing back into the sled, and it always pushes perpendicular to the surface, is I'm going to project that vector, because with vectors we can move them around, especially when they're acting on the same object, is I'm going to start it at the center, and I'm going to pull that normal force, which is perpendicular to the surface, and I'm going to project it down this way. So here's my normal force. So the force perpendicular to the surface. Now the way we're going to close this in is we're trying to find the magnitude of a force required to keep the sled keep the sled from going back down the hill. Well, the force is going to have to act parallel to the surface here. And so what I'm going to do is I'm going to close in this shape here. I'm going to draw a vector that is parallel to the inclined plane, and I have my surface. Well, the force vector and the normal force, because I have to be parallel to the inclined plane, forms a 90-degree angle. So I have a 90-degree angle inside of this triangle. Now, the other thing we have to do is we got to figure out, well, what would the angle be between the gravity and the normal force? Well, if I had a perfectly flat surface, the angle between the gravity vector and the normal force vector would be 0. But when I incline my plane by 60 degrees, I create a 60-degree angle between those two forces. So I have 60-degree angle in there. Now we can solve for what it wants. It wants to know what is the magnitude of the force required to prevent the sled from rolling down the hill. Well, we can use right triangle trig and use the sine function. Sine of 60 degrees is going to equal opposite, which is f, divided by the hypotenuse, which for this is 160. And so f is going to equal 160 times sine of 60. And that gives us 138.56 pounds. All right, so that's kind of a cool little problem here. All right, let's look at another one. We've got two more. Lawnmower is pushed a distance 200 feet along a horizontal path by a force of 50 pounds applied to the handle at an angle of 30 degrees to the horizontal. Find the work done. All right, well, remember, work, and we had a problem with this at the very beginning of this video, is equal to force times distance times cosine of the angle between force and direction. Well, the distance is 200 feet because it goes along a horizontal path. So distance is 200. It says the force is 50 pounds. That's how hard we're pushing on the handle. And so I just got to figure out what the angle is between the force and the direction of travel. Well, it says the lawnmower is pushed along a horizontal path. And the angle between the force is 30 degrees to the horizontal. So the angle between the force and the direction is 30 degrees. And so our work, in this case, is going to be 50 times 200 times cosine of 30 degrees, which would give us 8,660.25, and I'm going to say foot-pounds. All right, last one here in this video. All right, a car is parked on a driveway with an incline of 20 degrees to the horizontal. Parking brake applies a force of 650 pounds to prevent the car from rolling down the hill. I want to know what was the weight of the car. And find the force of that the car applies against the driveway. Okay, so we have to draw this picture, incline plane 20 degrees to the horizontal. All right, so dashed line for my horizontal. I'll get my incline plane here. So 20 degrees. We got a car that's parked on here. This is my car. And when I do that, I might as well go ahead and make my vectors here. So my car, it has the gravity vector that's pulling straight down here to gravity. And that's technically going to be the weight of the car. And we'll also have that normal force. Remember, there's a force that pushes into the box perpendicular to the surface. Now, I'm going to pull that normal force back down this direction. So there's my normal force. And the parking brake here is acting in this direction to keep it from going down the hill. So the parking brake applies that force of 650 pounds. So I come back down here into this triangle, and there's my parking brake force. And the angle between the normal force and the force parallel to the surface is 90, so I got a 90-degree angle in here. The force the parking brake applied was 650 pounds. So I know F was 650. We also know what the angle is in between the gravity and the normal force. It's the same as the angle of incline. So if I got 20-degree angle of incline, the angle between gravity and the normal force is also going to be 20. Now we can solve for whatever the part is we want. Well, the weight of the car, which is G, so the weight, is going to equal, well, I have to, and before I can get that, I have to use the sine function. So I'd say sine of 20 is equal to opposite, which is F, divided by G. And so I'd have G is going to equal 650 divided by sine of 20, which is going to give me a weight of the car to be 1,900.47 pounds. Now it also wants to know, well, what is the force applied against the driveway? So that is going to be the pushing perpendicular to the surface, which is the normal force line that I drew. So force perpendicular to the driveway applied, so force against driveway. Well, I'd have to solve for n. And to do that, we have a right triangle, so I'm going to say tangent of 20 is equal to opposite divided by adjacent. 650 divided by n. And so n is going to equal 650 divided by tangent of 20. And so the car is pushing against the driveway directly with the weight of 1785.86 pounds. All right, so